My name is Joe Farmer, and my colleagues are Sasha Rubinchek and Lloyd Hackle. We developed a new process known as HVLAD, which stands for High Velocity Laser Accelerated Deposition. This process is capable of producing coatings with exceptional corrosion resistance and extreme interfacial bond strength. HVLAD works very much like a conventional movie projector. You have a moving film that goes in front of a light source. In the case of HVLAD, this moving film is a high-performance coating material, such as tantalum, and it is bathed with a thin jet of water. The light source, instead of being a lamp, as we have in a movie projector, is a high average power pulse laser. This high average power pulse laser impacts the film and turns the water layer bathing the film into a plasma, as shown in frame 3. As shown in frames 4A and 4B, the plasma creates a very intense pressure pulse, which shears out a rectangular slab of film material. This film material is then accelerated at an oblique angle, striking the substrate at hypersonic velocity, as shown in frame 5. By striking the interface between the film and the substrate at an oblique angle at very high velocity, we have shear plastic flow. The shear plastic flow forms a highly localized, explosively bonded interface. By performing the HVLAD process, we're capable of producing the strongest interfacial bond strength of any known coating process. What's the opportunity with HVLAD? HVLAD has already been used to deposit corrosion-resistant refractory metal coatings with explosively bonded interfaces. Some additional R&D is required to enable the deposition of production-quality coatings that are continuous and completely free of defects. With that additional work, HVLAD should be relatively easy to deploy since it is based on commercially successful laser peening technology. What is our leadership position in this technology? First of all, Livermore has unrivaled leadership in high average power pulse lasers, as evidenced by the National Ignition Facility. High average power pulse laser technology has already been used for materials processing and has been commercialized in the form of the successful laser peening technology. Not only has laser peening been commercialized, it has also been deployed in mobile truck units. We can use the same technology with slight modification as shown in the last row of images in the slide to affect the HVLAD process. HVLAD will then allow us to produce coatings with local explosively bonded interfaces and the highest interfacial bond strength of any known coating process. How is HVLAD differentiated from other competing technologies? Unfortunately, conventional processes for the deposition of such protective coatings often require high temperatures, the handling of hazardous powders and chemicals that pose inhalation risks for workers, and lead to unacceptable porosity, poor interfacial bond strength, and problematic integrity for many applications. The proposed ambient temperature HVLAD process requires no chemical or powder feed and is capable of producing high-performance coatings with no residual porosity and ultra-strong interfacial bonds for application in a wide range of extreme environments. This is the ultimate additive manufacturing process. In this particular slide, we see the benefits of coating a surface with an HVLAD coating. On the left, you see micrographs of an oxide dispersion strengthened steel, which is good for use at very high temperatures after being contacted with a high temperature coolant, such as a molten fluoride salt. The molten fluoride salt, as one might expect, attacks the ferritic steel very aggressively, leaving the surface very much like Swiss cheese. On the right, we see the same surface protected with a HVLAD coating of tantalum. The tantalum prevents the attack of the oxide dispersion strengthened steel with this high temperature molten fluoride salt. By using an HVLAD coating, we have the best of both worlds, a corrosion resistant interface and a very, very high temperature structural steel, the oxide dispersion strengthened steel. And by using the HVLAD process, we also have an extreme interfacial bond without the fear of typical failure that we experience at such interfaces. In this particular table, we see a comparison of HV-Lad technology to other coating technologies such as electrodeposition, cold spray technology, and a thermal spray process such as high-velocity oxy-fuel deposition. Unlike HVOF, HV-Lad requires no powder feed. Unlike electrodeposition, no toxic chemicals are required. And unlike the high-velocity oxy-fuel process, HV-Lad can be conducted in air at ambient temperature without the fear of phase transformations in the substrate or coating material. What's the potential for profit from the HV-Lad process? In the United States, we lose billions of dollars every year due to corrosion. In the defense industry, we lose about $22 billion annually from corrosion. In the private sector, we also lose about $22 billion annually from the deterioration of our infrastructure, which includes things like steel bridges and pipelines. Protective coatings, such as HV-Lad coatings, could prevent this loss. We also know that the market in the United States for galvanizing and metallization is approximately $1.4 billion. So using these two sets of numbers, we can bound the commercial potential for HV-Lad somewhere between $1.4 billion and $44 billion. If you're interested in the HV-Lad technology, we encourage you to contact the Livermore IPO office. Catherine Elizondo is our licensing executive. Catherine's contact information is shown in this slide.